This is a presentation on emissivity by Professor Ronald Allen Newcomb, Adjunct Faculty, San Diego State University, College of Sciences, May 2009. In defense of the use of infrared thermometry on the desalination device on the CSL dock, which is my geothermal desalination laboratory. This presentation format has been modified for marine system inspections as of June 2012. What is emissivity? All objects emit radiation in the electromagnetic spectrum. The frequency emitted in that spectrum is determined by the energy in the body radiating that energy. Emissivity, symbol lowercase epsilon, is the ratio of the intensity of radiation compared to a black body, which is emissivity of 1 or 100%. So a 50% emissivity can be expressed as 1 to 50 or epsilon 50, or just an emissivity of 0.5. This is a dimensionless number. This number represents the object's emissivity rate, at which rate the object emits the energy that conducts to its surface. Different materials have different emissivity. Different wavelengths have different emissive properties. Emissivity changes throughout the range of temperatures as a body may experience because the energy released as thermal energy increases as the temperature increases, ergo the radiant energy is increased at the surface. The primary difference in emissivity is based on the respective surface condition, the condition of the various masses that it's emitting from. When the surface condition changes, the thermal properties change. The emissivity changes as well. All objects except theoretical bodies a la Kelvin emit radiation in the electromagnetic range. Again, when the surface conditions change, the thermal properties change. Polished stainless steel emits 7.5% of the infrared energy that strikes its surface, that comes to its surface through conductivity, and so has an emissivity of 0.075. Painting its surface with black enamel paint changes this to 80% emitted energy, or an emissivity of 0.8. This is why that paint has been used to equalize the various surface conditions on the device, as we shall see. The reason objects emit various wavelengths of light is because most atoms, when raised to a higher energy level, radiate higher energy levels of light as they throw off that energy of ever shorter wavelengths in order to return to a lower energy state, according to the zeroth law. Shorter wavelengths than infrared are visible down to the length of ultraviolet B wavelengths. Higher energy and shorter wavelengths, and we arrive at X-ray radiation, which require higher energy input. Longer than infrared, and we move into the microwave range, 104 nanometers. Most objects continue to radiate wavelengths longer than visible wavelengths at low and high temperatures, and therefore can also be seen with the thermal imaging devices, which can only see the infrared light. So even if they're higher energy and emitting visible light, they are still emitting infrared light because different molecules inside the mass have different energies. Emissivity also depends on factors such as temperature, emission angle, and wavelength. And a typical physical assumption is that a surface's spectral emissivity and absorptivity do not depend on wavelength. So the emissivity is a constant. This is known as the gray body assumption. It's valid if and only if we are discussing a very small range of wavelengths, such as the case when we are looking through a thermal imaging device. When dealing with non-black surfaces, the deviations from ideal black body behavior are determined by both the geometrical surface and the chemical composition and follow Kirchhoff's law of thermal radiation, that is, emissivity equals absorptivity for objects in thermal equilibrium, so that an object that does not absorb all incident light will also emit less radiation than an ideal black body. Note that most emissivities found in handbooks and on websites of different infrared imaging and temperature sensory companies are the type discussed here, total emissivity. A technical distinction needs to be made that the wavelength-dependent or spectral emissivity is the more significant parameter to be used when one is seeking an emissivity correction for a temperature measurement device. This is corrected by modern instrumentation, both thermometry and thermal imaging devices, by the device themselves in the software that runs the system. Infrared cameras, thermography devices, have lenses and/or detectors that are sensitive only to the longer infrared frequencies, those in the 10.4 to 12.5 nanometer range, those considered to be in the thermal range of infrared. This technology can help us analyze the objects and indicate whether the objects are functioning as designed or if they are emitting excessive heat for some reason and therefore need improvement or modification. When properly calibrated, they yield reliable data. The infrared thermometer we use is calibrated using the direct measurement at the lab using a direct measurement probe, which you will see shortly. Methodology. Note on the two pipes visible at the left the two black paint spots that were used to take thermal measurements. The black enamel paint normalized, equalized the two emissivity rates of these two pipes. The upper one, carrying colder water, oxidized faster than the lower one, giving a different emissivity for each one. This black paint enamel normalized the emissivity to 0.8 to ensure accurate measurements. Here we can see the direct measurement device, an instrument that its probe had been put directly into the hot water, and then the thermometer was calibrated to that to ensure accurate measurements. Textured 316L stainless steel has an emissivity of 0.35 nominally, but when the emissivity changes, as in this case, when these pipes have been left outside and used to carry different thermal gradients of water, one quite cold, one quite hot, they emit different amounts of radiation, again corrected by the black enamel paint. In the lower right you'll see that water purity was tested in this device by a third party, that is, a student from the university who took the water directly from the output pipe and put it into the testing bottles to send off to independent labs. They were also tested by San Diego State University laboratories and, of course, correlated with those, and they were within acceptable ranges of variation. In our methodology of testing the evaporation, condensation, desalination units that we tested over several years, we used infrared thermography to test the system efficiency, how much insulation would be would be used on the finished device should it be commercialized. They were not, but they would have been thermally insulated, and where that insulation went would have been an important aspect. Secondly, infrared thermometry was used to test the energy metrics, to take energy metrics for determining how many BTUs, how much energy was it using per gallon of water produced. And then the water quality was taken. filtered ocean water from Scripps Institute was used. It was contaminated with harbor seal coliform bacteria from La Jolla Children's Pool and then tested by 2 independent labs and San Diego State University, as well as the County Medical Health, to see how well that water was purified. The prototyping history of these devices included 5 distinct prototypes and modifications of each. Prototype 1, conceived and designed in 2003 and tested in 2005, experienced 3 modifications before Prototype 2 was built in 2005. It also went through 3 modifications. Prototype 3 was designed and built at the laboratory in 2006. There were 2 modifications of it. Prototype 4 was tested from late 2006 to 2007. That was currently the device when this paper was originally put together and presented. And then Prototype 5 was later done in 2007. At that time of future, as it states here, and the tests were completed in 2007. In summary then, emissivity changes are well understood. Correcting emissivities of the various materials allows for accurate metrics to be taken. The metrics were accurate within tolerances. Testing included calibration of the devices by direct measurement taken on site. The instruments were calibrated and emissivities were adjusted. Devices to date were energetically inefficient. Newer binary generation techniques and RO membrane improvements during the test period itself made these devices obsolete while they were being tested. Additionally, the original inventor misunderstood heat flow from geothermal wells, also making the device obsolete and inefficient for use as a geothermal desalination technology.